we'll record. And we are going to be posting the lecture or the seminar to the IMSE website later for people that aren't able to join us today. But thanks everyone that was able to join us today for this seminar. This is the first live IMSE seminar for the semester. We are also, as the students know, and as many of you know, we're participating in the North American Materials Council's seminar series. Those seminars are being held on Thursdays and Fridays, where there are live Q&A sessions after the recorded presentations. And so students that are participating today, thank you for joining us for Dr. Wren's seminar today. This meets your obligation for this week, but if you're still welcome to watch the NAMCS seminar later this week if you're interested. And those of you faculty that are on the seminar, those Materials Council seminars are actually posted. Most of those are also recorded and posted. If you're interested in catching up on some of the old ones, they are available. So again, I want to welcome everybody to today's seminar. Our speaker today is a new faculty member in the physics department, Dr. Sheng Ran. He's an assistant professor of physics, and his seminar title today is Spin Triplet Superconducting State in the Nearly Ferromagnetic Compound Uranium Tellurium-2. I'll ask Dr. Ran to introduce himself and introduce his background a little bit more, but I do just want to note that his research lab that he's currently building here at WashU is dedicated to the discovery, synthesis, characterization, and control of novel quantum materials with emergent electronic and magnetic states. And so that'll be part of what he talks about today. So Dr. Ran, please tell us a little bit about your background, and we look forward to hearing your talk. And you should be able to share your screen so that everybody can see the slides.
Yes. Okay. Well, thanks for the introduction. I'm very excited to give this talk. Part of the reason is my lab is under construction. So, as Kathy said, I'm a new faculty member here. So I'm really recruiting students. So I'll see if any of you get inspired to join my research group. Okay, so I did my PhD in Iowa State University, and I worked on the iron pnictide for a majority of my PhD study. Then I did 2 postdocs, first in UCSD, working on heavy fermions, condo systems. And then I moved to University of Maryland, did a second postdoc. There I worked on all kinds of topological stuff. And here, this talk is mainly about the discovery of new topological superconductivity. Actually, this is more or less the same talk I gave for the interview. So those of you who already attended my talk for interview, you won't miss much if you watch cell phone or something else. Okay. All right, let's start. So, okay, all right. So my son is 7 now, and my daughter is 5. And once in a while, the kids ask you, well, Daddy, what do you exactly do at work, right? So I made this story. A long time ago, there was an island. It's called Singlet Island. On this island, there's a special creature, and those are called superconducting man. Not the Superman, superconducting man. Just like Superman, superconducting man also have some special superpower. So we humans are very interested in this superpower. We want to find them and learn their superpower and build machines out of this. So generations of explorers have landed on this island, and they found many interesting things. For example, on one side of this island is extremely cold. The other side of the island is very hot. But this superconducting man, they only live on the hot side. And notice that on this island, there's some mountains. On this mountain, they're very afraid of this bar magnets. Now, I also spend some time on this island, but well, then we decided, well, together with a few colleagues, we decided to took on a boat and we started a new journey. So it turns out we landed on a new island called Triplet Island. All right. So on this new Triplet Island, we also found a superconducting man. But the superconducting man we found here is very different. One of the biggest difference, they're not afraid of this high mountains. As a matter of fact, the one I'm gonna show you today, those superconducting men, they live on one of the highest mountains in the world with strongest bar magnets. So clearly, they have a different superpowers. So we're very excited about this. Well, so that's the story I made out for my kids. After hearing the story, the kids nodded and said, "Oh, Daddy, you did a good job." And okay, all right, there's something. So today, basically, what I'm going to tell you is a real life story of this this merger. But before I start, I have to mention this work. I'm new faculty member here. This work was done when I was a postdoc. So a lot of people participated. Here is my postdoc advisor, Dr. Nick Butch from University of Maryland, and NIST, and a few graduate students and postdocs. This is Dr. John Paglio, very important collaborator at the University of Maryland. And majority of the work was done in the National High Magnetic Field Lab. So there we collaborated with Dr. John Singleton and David Graff. And the STM work was done in collaboration with Vidya from UIUC and his postdoc. Dr. Eiji Furukawa from IMSE Lab did NMR work for us. All right, so a little bit of background. Now we know for a superconductor, you can have spin up, spin down pair. That's called a Cooper pair. Now, because the entire wave function has to be is fermions, so it has to be antisymmetric. If you have spin up, spin down pair, the orbital part of the wave function has to be symmetric. Therefore, you have S wave or D wave. Now, later on, people start to think, can we have spin up, spin down pair, spin parallel spin part? And it turns out you can. For example, in helium-3, it's not a superconductor, but it's a superfluid. You probably have this parallel spin pair. And in that case, the orbital part will be antisymmetric and therefore, for example, P wave. Now, turns out this spin parallel or triplet spin superconductors is a very rare quantum phenomenon. So far, we discovered about 10,000 superconducting compounds. That includes all the dopings for iron pnictide and the cuprates. But within this 10,000 compounds, there are probably like less than 5 are really candidates for a spin triplet pair. It's a very rare quantum phenomenon. But recently, in the past 10, 20 years, it started to have more and more attention on this. The reason is related with this so-called Majorana fermions. So Dirac wrote an equation to describe the particles, and this Dirac equation predicts that all the particles has antiparticles. For example, electron has positron, neutron has antineutron, proton has antiproton. But if you, from mathematically, the particle and the antiparticle is just a complex conjugate of the psi, the wave function. And Majorana says, well, if the solution to the wave function, if it's a real number, then a complex conjugate of a real number is itself. So Majorana predicts that there must be a whole class of particle where the antiparticle are themselves. So these are called Majorana fermions. So mathematically, we can just write it up like this. It's going to be delta C delta plus C or C delta minus C. If you do the complex conjugate, you get the same thing. What does this mean? That means Majorana fermions can be think of as an electron or a hole in a condensed matter system. Well, this is just a C dagger plus C. If we in the condensed matter system, if we have a mixture of electron and hole, that might be a Majorana fermions. And this can be found in a superconductor. If we know, everyone, I hope everyone will agree me on this equation. So electron equals to electron plus a hole, because electron and hole are particle and antiparticle. They cancel with each other, then you just have electron equals to electron. But, so this is for just a normal condensed matter system. But if we have a superconductor, we know an electron and electron will form a Cooper pair. Not only they form a Cooper pair, there are a lot of a condensate of Cooper pair. So if you just add one more Cooper pair, it doesn't matter. It all goes to the condensate. So the net effect is that electron equals to hole. Then you can have a mixture of electron and hole at the same energy. But what we really need is not just Majorana fermions. What we need is a Majorana confined as a zero energy, therefore called a Majorana zero mode. So imagine we have a superconducting gap like this, and at some point, if we have a vortex, so this is just like a quantum well. We can solve this quantum well. We can get energy levels. It may be complicated, depends on details, but one thing is for sure, that is we cannot have energy level at zero energy. There's always a zero point motion. In general, all this quantum well, you do not have energy state at zero energy. But someone proposed that if you have a p-wave superconductor, so triplet superconductor, the barrier phase collected when you go around will cancel the 0 point motion exactly. In that case, we can have a energy level at the zero energy. Therefore, we can have, in principle, we can have a mixture of electron and hole at zero energy level. Therefore, a Majorana fermions at zero energy level. So the motivation is very clear. We want to find triplet superconductors so that it can host Majorana zero mode, and everyone knows that that's the building block for quantum computation. But where can we find a triplet superconductor? To be honest, we don't even have a good practical guidance to find a normal superconductor, let alone a triplet superconductor. The only guidance we have so far in the community is based on these two phase diagrams. So on the left is a cuprate, on the right hand is iron pnictide. In both classes, the parent compound actually is not a superconductor. It has antiferromagnetic ground state. Now, if somehow you can suppress antiferromagnetism by chemical substitution or by applied pressure, you suppress antiferromagnetic enough, then you have a lot of ferromagnetic fluctuations, and turns out that fluctuations can induce superconductivity, and those are unconventional. So a lot of people are working under this practical guidance. Actually, my PhD time, I devoted a lot of time on this. So the idea is get a ferromagnetic compound, try chemical substitution or apply pressure, and just measure resistance. If it's not a superconductor, try another one. But this will not help us to find a triplet superconductor, because we know, well, cuprate is D wave, iron pnictide is S plus minus wave, both are spin singlet. And this can be understood in a very simple picture. If we believe the underlying antiferromagnetic fluctuation is important for the Cooper pair, then the antiferromagnetic has alternating or spin up, spin down. No wonder the fluctuation will only gives you this type of pairing. If we're looking for spin triplet pairing, likely we need to look for superconductivity in the vicinity of ferromagnetism. So that's really the starting point of this whole project. That is to look for superconductivity in the vicinity of ferromagnetism. And indeed, there are already such materials. There's a whole class called ferromagnetic superconductors. So here I'm showing 3 compounds: uranium germanium 2, uranium rhodium germanium, and uranium cobalt germanium. In all these 3 compounds, in some region, we have coexistence of ferromagnetism and superconductivity. In uranium rhodium germanium and uranium cobalt germanium, the superconductivity even happens at ambient pressure. In uranium germanium 2, you have to apply some pressure to suppress the ferromagnetic, then you induce superconductivity. Well, if you look at the 3 compounds carefully, you might notice that all the 3 compounds contain uranium. Well, of course, it contains germanium too, but we believe both the superconductivity and ferromagnetism comes from uranium. So it occurs to me, well, why don't we just look for superconductivity in uranium ferromagnetism? So, ferromagnetism contains uranium. That's a very good starting point because we have 60,000 inorganic compounds. If we focus on just ferromagnetic compounds containing uranium, then you shrink the space to only a few hundred compounds. That is durable. We actually looked for many ferromagnetism containing uranium. For example, uranium cobalt alumina and other few compounds. And this time, the target was uranium-7 tellurium-12. So this is a ferromagnetism. You can see the Curie-Weiss temperature is about 50 K. So, well, let's make it. Well, turns out, the first few times when I try to make this compound, I keep getting a different compound. It's from X-ray, you can see this is uranium ditelluride. So instead of uranium-7 tellurium-12, I keep getting uranium ditelluride. But you really get very nice single crystals. And from the Lowy pattern, you can see very nice Lowy pattern. So clearly you want to do something on this. But let's see what has been done. It turns out this compound has been studied for decades. From 1960s, 1970s, the magnetic property were already studied in the 1960s. And single crystal were made in, this one was in single crystal, was on single crystal. So in 1999, the single crystal were already made. And in 2006, there is a pretty comprehensive study of the thermodynamic, transport, and magnetic study on this. So what was known? Okay, here is resistance as a function of time. You can see this is a very standard uranium heavy fermium compound. So at a high temperature, resistance slightly go up due to the single ion condo effect. And at the lower temperature, there's a condo coherence. Therefore, the scattering becomes coherent, resistance drops. And from magnetization, if you look at the B-axis, it's Curie-Weiss behavior at a high temperature. At about 50 K, the magnetization drops, again, likely due to the condo coherence. And they measure the specific heat, the gamma, which is proportional to the effective mass. The gamma is about 150 millijoule per K square mole. So in the old days, if it's about 400, people will call it heavy fermium. But nowadays, even if it's larger than 100 millijoule per K square mole, people will call it heavy fermium. So if you use that criteria, this is a heavy fermion compound. But one thing you notice, there is no magnetic ordering. So to summarize, the resistivity, magnetization, specific heat were carried out down to 2K. It's just another heavy fermion compound, and there is no magnetic ordering, and we don't like you at the moment. But if you think of this a little bit more carefully, it's a boring system, but it's interestingly boring in a sense that it contains uranium. So for those who are not familiar with this, uranium is at the bottom of the periodic table where everything contains F electrons. So at a higher temperature, all these F electrons, they point to all kinds of directions. But the system wants to release entropy at a lower temperature. Now, of course, the Kondo effect is a one way to lose entropy, but given that gamma is only 150, it's large, but not that large, it really indicates there are still unscreened moments. Those unscreened moments at the lower temperature, they would like to, get into an altered state to release entropy, either an antiferromagnetic ordering or a ferromagnetic ordering. So when I saw this, I really think there must be a magnetic ordered state if we cool down a little bit more. So can we do this? Yes, we can. So first we measure specific heat. Here I'm showing specific heat as a function of temperature for above 1.8. This is very consistent with literature report. Now we can cool down this a little bit more. And when you do this, well, there's an anomaly indicating indeed there is a phase transition below 2K. What is this phase transition? So we did AC magnetization. In dual magnetization, well, this really looks like a textbook Meson effect. It looks like a superconductor. Okay, let's measure resistance. Here I'm showing resistance as a function of temperature. You can see below 1.5 or 1.6K, the resistance goes to 0. Indeed, this is a superconductor. So I was looking for a magnetic ordered state. It turns out we got a superconductor. Well, one thing already indicated the superconductivity is unconventional. So here, we can grow these samples with two different methods. We can grow it with chemical vapor transport, or we can grow it with flux. Here, I'm showing the resistance as function of temperature for two different methods. If you grow with chemical vapor transport, you can see it really goes to 0. But if you grow it with flux, the triple R, so the resistance at the room temperature divided by the resistance at the lowest temperature, that triple R is only 2, indicating there are a lot of impurities or defects. In that case, it does not go to superconducting state. This indicates the superconductivity is very sensitive to either impurity or defects that likely is unconventional. Well, let's look at the specific heat a little bit more carefully. Here, I'm showing specific heat divided by temperature as a function of temperature. But here, I took off the contribution from phonon, and therefore this is only electronic contribution. A few things is very interesting. First, there is a residue gamma. Okay, this gamma again is proportional to the density at the Fermi level. So if this is really a fully gapped superconductivity, or everything becomes superconductor, then there should not be any residue gamma. But here it's showing half of the gamma value at normal state in the room at above 2K. Half of the, indicating likely half of the compound did not go to superconducting state, or maybe it's a bulk superconducting state, but half of the electrons still remain Fermi liquid. All right. The second thing is below the superconducting transition temperature, if it's a BCS superconductor, this the specific heat should really go as an exponential law. But here it goes as a power law, and the power is like a T cubed. So that indicates there is a point noise. And the third thing you might notice is the entropy is not conserved. So if we do the integral beneath this curve, that gives you the entropy. But notice this portion and this portion, in an ideal case, they should be balanced, but here the entropy is not conserved. So what's going on? So we made a specific heat to even lower temperature. This is down to about 80 milliK. It turns out there's an upturn at a very low temperature. And this upturn we checked, very likely it's not from nuclear Schottky. So we checked, we use tellurium isotope. And with different isotope, you still get the same effect. So likely this is not from a nuclear Schottky. But nevertheless, if we took off this upturn, and if we subtrate this upturn, then of course C over T will go to 0. You subtrate, you took off that the divergent part, but also the entropy is now conserved. But why this is diverged? This divergent term, this is still a mystery. And recently I talked to a theorist, and when he saw this, he was very excited because this part in our fitting, it goes to like a T to 2/3. T to 2/3 in specific heat is a smoking gun for the spinless quantum spin liquid. So if indeed, so there's a possibility that uranium ditelluride, besides its superconductivity, it might also, the normal state might actually be a quantum spin liquid state. If really this is quantum spin liquid, this will be the first example of a metallic quantum spin liquid. But this is still a hypothesis. All right, we can do thermal conductivity to look at the energy gap a little bit more carefully from that. Again, if this is BCS theory, BCS type of superconductor, this term, this quantity should go to 0 exponentially. But here it's parallel. And again, this is consistent with a node on the gap. But all of this are not the most exciting part. The most exciting part comes when we put this under magnetic field. Since there are some students who are probably not so familiar with superconductivity, let me give you a little bit of background. When we apply the magnetic field to a superconductor, it will suppress superconductivity. And it suppresses superconductivity in 2 different mechanisms. The first mechanism, we talk about the Cooper pair, likely spin up, spin down pair. When you apply the magnetic field, due to the Zeeman effect, it wants to flip one of the spin, and therefore it breaks the Cooper pair. Or, so this is called paramagnetic effect. Or, when you apply the magnetic field, the electron is gonna go in a circle, therefore gain kinetic energy. If the kinetic energy is too large, and that might overcome the condensation energy, and therefore breaks the Cooper pair. So this part is called orbital effect. The bottom line is magnetic field will suppress superconductivity. So we can check this. And uranium ditelluride is orthorhombic system. So in principle, A, B, C are all different. So we can play the game by applying the magnetic field along all the 3 axes. If we apply the magnetic field along A axis, this is what happened. So indeed, by 6 Tesla, we suppress the superconductivity. If we plot the critical field as a function of temperature, this follows the WHH curve very well. So indicating along this along this axis, really the orbital effect is dominant. And the paramagnetic limit is about 3 Tesla in this compound. Now, if we apply the magnetic field along the z-axis, you can see, it starts to deviate, but not too much. This is what happened if we apply the magnetic field along the b-axis. First, we can see even in 20 Tesla, this is still a superconducting compound. So actually, by 20 Tesla, it's only enough to suppress superconductivity from 1.6 K to 1 K. So this is a super large critical field. Now, if we plot on the same plot, it's going to be here. So 20 Tesla is here. It significantly deviates from the orbital effect. Well, 20 Tesla was already the maximum field we can apply in the lab. So in order to know how high the critical field really is, we took the sample and we did experiment in National High Magnetic Field Lab. So here I'm showing the resistance as a function of magnetic field. We can see it's all the way 0 up to 35 Tesla. And then all of a sudden there's a wall, so it goes to normal state. So the critical field at 0.35 K is 35 Tesla. This is, if we plot on the same plot, 35 Tesla is here. To give you a comparison, last year people discovered room temperature superconductivity. This is lanthanum hydride under pressure, and the critical temperature is 250. That's room temperature at some places. So the critical temperature is such high, and the critical field is about 140 Tesla. Now here, our compound, the critical temperature is only 1.5 K, but the critical field is 35 Tesla. If we would scale the critical temperature, then the critical field for uranium ditelluride will be 5,000 Tesla. This is incredibly high. Now, there are many possibilities you can have such high critical field, but one of the possibility, actually we rule out most of those, and the one that remains is the following. We can have a spin up, spin down pair. In that case, if you apply the field, as I mentioned, due to the Zeeman effect, we split one of the spin and break Cooper pairs. But what if you start with a spin triplet superconductor? The two spins are already in the same direction. In that case, Zeeman effect, at least the Zeeman effect will not play a role. So at least it will not controlled by paramagnetic effect. So is there any evidence? One way to prove the spin susceptibility is the so-called NMR measurement. So NMR 9-shift directly measure the spin susceptibility. If this is a spin singlet pair, at high temperature, we have spin half electron. At the lower temperature, two spins, spin up, spin down, gives you total spin 0. Spin susceptibility is supposed to decrease and eventually go to 0. But if you have a spin triplet pair, or high temperature, you still have spin half electron, but lower temperature, at least along certain directions, two spins are parallel, gives you total spin 1. Two electrons give you total spin 1. So the total spin susceptibility is going to stay the same. This is what we have when we did NMR with the collaboration. So indeed, NMR 9-shift stay constant for the entire temperature range. But of course, this was done for the powder, and many things were not clear. For example, the 9-shift is supposed to have spin susceptibility and the orbital contribution. So later on, a Japanese group, they did a more careful study on single crystal samples. So they ruled out the orbital contribution. The orbital contribution is supposed to increase with magnetic field. They did the 9-shift in 1 Tesla and 3 Tesla. They do not see significant change. Therefore, they think the orbital contribution here is very tiny and negligible. Here, they did see a tiny drop, but this drop is not enough for a spin singlet pair. So on this insect, for a spin singlet pair, the drop is supposed to be this large. So here, even though they see a drop, this is still consistent with a spin triplet superconductors. All right, so indeed, we found a spin triplet superconductor. Well, the next question is, can we, find the physics that you promised at the very beginning? So we did STM study in the collaboration, and here I'm showing the STM study when they put the tip in the bulk. When they put the tip in the bulk, here you can see there's 9 tip indicating the superconducting energy gap. But they can also put the tip as the edge of the sample. So it's a layer, it's kind of layered samples. They're different layers. They can put the tip as the edge of the layers. When they did this, depending on which edge they put the tip on, you see this anti-symmetric in-gap state. So these are still within the superconducting state. They see this anti-symmetric in-gap state. Now, the origin of this anti-symmetric feature is still under debate, but one thing is clear: there is a chiral edge state, right? Topological superconductor is a direct analogous to quantum Hall. For quantum Hall, you have insulated state as edge, you have conducting edge state. For a superconductor, you have superconducting bulk state. What can you have on the edge? And likely this chiral edge state is due to Majorana, the chiral propagating Majorana fermions. But again, the origin of this is still under debate. Okay, if indeed we have a chiral surface state, then you should have a time reversal symmetry breaking inside the sample. So do we really have a time reversal symmetry breaking? Again, we did this with the collaboration with people in another group. This was done in Stanford. We did Kerr effect. So Kerr effect will tell you whether you have time reversal symmetry breaking inside the sample. So you have a polarized laser beam. If there is time reversal symmetry, you will have a non-zero Kerr shift. Here, turns out 1.5 is TC. Below TC, indeed, you have non-zero Kerr shift. But turns out the sample has time reversal symmetry domains. If you just shoot light on the sample, likely the domain size is smaller than the beam size. So you will get average. And therefore, at the beginning, when they shoot the light directly, they actually did not see time reversal symmetry breaking. But what they did is they applied the magnetic field when they cool the sample down to train the domain, basically to align all the time reversal symmetry domain along the same direction. And when you get to the base temperature, they turn the field off, and then they start to do the measurement. So when they do the measurement, there is no magnetic field. They use the magnetic field to align the domain to all the directions before the measurement. Depending on which direction you apply the magnetic field for this training field, you can get different size of the Kerr shift. Then people were a little bit confused at the beginning because this is really an orthomic system. So all the irreducible representation are one-dimensional. You're not supposed to have a time reversal symmetry breaking. Like a strontium ruthenate is a tetragonal system. Then you can have px plus ipy. But here is an orthomic system. One possibility is that you actually have 2 different autoparameters, and they have very close energy levels. If that is the case, we should be able to see in specific heat. So once we saw the Curry effect, we went back to measure specific heat with a final temperature increase. And indeed, when we do that again, we see in specific heat, there are two superconducting transitions, indicating two autoparameter that has a very close energy levels. All right, due to time, I'm gonna skip this part. But one thing I want to say is, this really inspired a lot of research activities in the community, and a lot of paper came out in the past year or so. Here I just put a few, the original ones. And up to this point, I hope I made it clear that this is a very exciting discovery, but I discovered by accident. Well, when I say by accident, I don't really mean I was having a vacation and pick up something from the floor. It turns to be a triplet superconductor. By accident, what I really mean is this: we were looking for India, and we got a new continent. Well, it turns out this new continent is also a very interesting platform to study some fundamental properties of superconductivity. So here, I talked about this. There are two mechanisms to suppress superconductivity. The bottom line is, well, superconductivity will die in magnetic field. But in the next, I'm going to show you three reentrant superconducting state in a triplet superconductor. Here, reentrant means die and come back to life in magnetic field. So after the study, National Magnetic Field Lab, they wrote an article calling this a Lazary superconductivity. And I was completely off. I didn't know what Lazary was. And turns out, this is a story in the Bible. Lazarus died, and Jesus came and raised him from the dead. So here, I'm going to show you how magnetic field raised superconductivity from the dead, and for 3 times. So here, I showed you this data. I'm just plotting it in a logarithmic scale. So resistance as a function of field. It was 0 up to 35 Tesla. Then there's a 5-order magnitude jump. Here, this is when we apply the magnetic field along the b-axis. Now, we don't have to apply the magnetic field along any spatial axis. We can rotate it from b-axis, for example, towards a-axis. When we do that, you can see at some small angle, the resistance was 0, and then at 15 Tesla, it goes to a normal state, and then it comes to 0 again, and eventually this goes to normal state. So this is exactly called field-induced superconductivity. Well, this field-induced superconductivity is a surprising phenomenon, but this has been seen. Here I'm showing 2 compounds, one inorganic compound and an organic compound. In both compounds, you have some superconductivity and goes to normal state and goes to superconducting state again. But in these 2 compounds, this has been understood in terms of so-called Jacquarino-Peter effect. Given the time, I'm gonna skip this. The bottom line is this was understood. And there's another similar case, uranium, rhodium, germanium. This is one of the ferromagnetic superconductor. So for uranium, rhodium, germanium, again, you have superconductivity and goes to normal state and goes to superconducting state again. And here, people believe ferromagnetic fluctuation is playing a role for this field-induced superconductivity. Now, recently, someone proposed a different mechanism for this field-induced superconductivity based on the 2D, based on the band structure. So this uranium telluride, even though it's the sample looks 3D, when we do the DFT calculation or the RPS measurement, you can really see there are 4 different sheets on the band structure. They're basically 2 parallel sheets, 2 pairs of parallel sheets. It's like a quasi 2D band structure. Based on this quasi 2D band structure, someone proposed that if you have a quasi 2D structure, when you apply the magnetic field, when the field is really strong, you can confine the electron within the plane, and therefore you do not have a closed orbits. In that case, the orbital effect will not play a role. Then you can have field-induced superconductivity. But nevertheless, so we see field-induced superconductivity. Well, first, this has been seen, and second, someone can explain this within their theory. So it's not the best. Here, I'm gonna show you something that's really unique to this compound. All right, so I showed you this data. I'm showing you again. You have 0 resistance up to 35. It goes to a normal state. But we want to ask, what kind of normal state this is? So with the magnetization study, here we can see in the magnetization along the b-axis, it linearly increases, and there is a sudden jump in the magnetization, indicating likely the magnetic moment was along a different axis. When you apply the magnetic field along this axis, at 35 Tesla, all of a sudden it rotates to this direction, and therefore that gives you a jump in the magnetization. This is a hypothesis. So we call this state a field-induced ferromagnetism. And this was convinced by another group. So here, this is a complete angle phase diagram. So I'm showing a magnetization, magnetic field, and as function of angle phase diagram. So we have 3 different phases: superconducting state, re-entrant superconducting state, and beyond 35 Tesla, there is a field-induced ferromagnetism. Yes. But in some spatial angle range, here in about 25 degrees from b-axis to c-axis, there is another field-induced superconducting state. And this angle range corresponds to the norm of the 0, 1, 1 direction. Okay, so here is the resistance as a functional field. We're applying the field in some arbitrary direction from b-axis towards c-axis, about 14 degrees. Then you see superconducting state goes to normal state, goes to this field-induced ferromagnetic state. If you keep increasing the field, this is what happens. So at 23 Tesla, at 23 degrees, you see at 40 Tesla, all of a sudden the resistance goes to 0 again. If you keep increasing, eventually this feature goes away. So here I'm showing a second field-induced superconducting phase, and this is the only compound within 60,000 inorganic compound. This is the only one to show 2 different field-induced superconductivity. And the second one is the world record. So the director of the National High Magnetic Field Lab made a comment on this. He says this is likely to be among the most important discoveries to emerge in their high magnetic field lab in their 25 years of history. And recently, okay, if you look at this, someone says, well, the resistance really didn't go to 0, but this is likely due to the noise in the pulse field. Recently, a Japanese French group, they repeat this experiment again, and indeed, the resistance goes to 0. Okay, so for this phase, as far as I know, there's no good theory to explain why that happens. What's more striking, there's actually a third field-induced superconductivity, and the third one is under pressure. Okay, given the time, I'm gonna skip all this phase diagram. I'll just say the superconductivity get enhanced under pressure and it goes to about 3K. The TC goes to 3K at a very high pressure, not very high, relatively high pressure region. We have a magnetic phase. Now, in the middle, we have a coexistence of magnetism and superconductivity. But in this region, if you zoom in, you will see the resistance actually did not really go to zero. In this part, now, if we apply magnetic field, we'll have non-zero resistance goes to zero and comes back to normal state again. So that's the third field-induced superconductivity. All right, so having one of this is surprising. Having two of this is astonishing. And having three such phases, that's really too good to be true. As a matter of fact, on a conference, a French scientist, he came to me and said, well, if you report another field-induced superconductivity, we're not going to believe you. All right, so that's all I have for this. But for myself, I really have a motivation to come to give a talk. That is to do two advertisements. And the first one, as Kathy mentioned, I'm a new faculty member here. We're start to build a lab, and really, we need an undergraduate student and a graduate student. If somehow you got inspired to work on the quantum materials and all this exotic phases, please don't hesitate to talk with me and join the group. And second advertisement, going back to the story at the beginning, the kids really like this story. And also during the COVID time, I spent a lot of time at home with kids. So I started to make up more stories. So in the end, I ended up publishing a book. And this is the first book of a series that I'm planning. And basically, the story was made together by me and my kids. The idea is to use a story that kids can understand and use a story to introduce the quantum physics. If you have kids, this book can be found on Amazon. If you search Quantum Island Real Friendship, you will find it. All right, that's all I have. And if you have any questions, please.
All right, so thank you very much for a really interesting seminar. I'm very entertained by your children's book. We'll have to go and check that out. So we'll go ahead and open it up. We've got about 5 minutes left for questions. So if you'd like to ask a question, we've got a small enough group here that I think you can just go ahead and unmute and feel free to ask. So I see that Jim unmuted, but I don't hear him.
Well, I don't want to be first.
Well, you unmuted, so now you are first.
Okay, well, a very nice talk. I wish I were still in St. Louis when you joined the faculty. Okay, we'd have a lot to talk about. You talked about uranium tellurium-2, and I note that pure uranium in the beta phase also is superconducting at 0.8 Kelvin, and if you use pressure and bring it into the alpha phase, it's about 2.4 Kelvin. Is anything, what's known about pure uranium superconductivity? Does it have anything to do with perhaps triplet superconductivity, or does one know?
Sheng, you're muted.
Oh, okay. Well, sorry, I wasn't aware of that the uranium goes to superconductivity. No, I don't know this. I'll look into this.
Well, certainly under pressure, but
Under pressure.
Um,
Okay. All right. All right.
another,
I'll look.
I don't have the, let's see, the reference for it, but I can send you that. And,
Yeah,
and maybe
yeah,
it's
that's
wrong. I mean, if you don't know about it, it's probably wrong. So, but
Well, you know more about all this uranium.
I'll check on that. Uranium and neptunium are quite similar. The 4f orbitals are quite extended. And so one might expect to find similar behavior in neptunium systems and compounds. And might that be a place to look for future triplet superconductors also?
You said plutonium?
Neptunium.
Neptunium. Okay. All right. Well, that one is more radioactive than uranium, right?
I don't know much about your radioactivity, so
Yeah, uranium activity is pretty low.
yeah, it's just alpha, I think. So you don't.
Right.
Yeah, I don't know about neptunium. Yeah,
That one is pretty radioactive. Yeah.
Yeah, plutonium you don't want to mess with. That's next to
Right.
neptunium.
Right.
Okay, well maybe that's why it hasn't been studied so much. Okay, that was my question.
All right, thanks, Jim. Any other questions?
I'll ask more of a practical question. For one, I just tend to avoid everything from the bottom of the periodic table. Anything around uranium and plutonium and neptunium, I tend to just stay away from. But I had more of a practical question. So a lot of the research you were talking about was conducted at like really low temperatures.
Right.
And I was just interested in like how you actually can consistently get temperatures that low and how difficult it is to actually maintain those types of temperatures.
Okay. Well, nowadays the technique is pretty good. So I mean, in the dew fridge, you can go to, in principle, you can go to even 10 milli but we can go to at least 50 milli or 80 milli pretty easily. In the old days, the dew fridge is really hard to operate, but nowadays the new ones is just you click buttons and it will automatically go there and it can maintain the temperatures.
Okay, good. Any other questions? All right, we're slowly losing people here, so I think we'll go ahead and end it here. So I want to thank Dr. Rand again for presenting the seminar today. And again, the recording of the seminar will be posted on the IMSE website. So if you know somebody else who might be interested in watching it, we'll be making that available. I also want to remind everybody that we are going to have a couple more internal speakers over the course of the semester. And those announcements will come out. Beth Garton will send those around in addition to the announcements of our usual North American Materials Council seminar series for the semester. So thanks again for everybody for coming. Thanks again to Dr. Rand for giving the seminar today.
All right. Thanks, everyone.
Thanks.
Thank you.
Bye-bye.